Welcome all. In this lecture, I am going to discuss about web packets, and this lecture is from the textbook of in JTD. In this lecture, I will discuss about the basic concepts of web packets, the mathematical preliminaries behind the web packet, the structure of web packet, and the Heisenberg's uncertainty relation and its link with the wave packets. In classical physics, a particle is well localized in space. For its position and velocity can be calculated simultaneously to arbitrary precision. So to describe a particle, we know that in mechanics, two quantities, that is position and velocity, these are needed. If we know the values of the position and velocity, then we can define the dynamics of the particle with precision. However, for quantum mechanics, it describes a material particle by a wave function corresponding to the matter wave associated with the particle. We know that in quantum mechanics, if we want to describe a material particle, then we need the concept of wave function. And the name is wave function. So what wave? This is matter wave. As proposed by de Broglie, that particle has dual character, that is wave character and particle character, and lambda is equal to h by mv. We all know about de Broglie's equation. Wave functions, however, depend on the whole space. Hence, they cannot be localized. So, wave function is not localized, but they depend on the whole space. If the wave function is made to vanish everywhere except in the neighborhood of the particle or the neighborhood of the classical trajectory, it can then be used to describe the dynamics of the particle. That is, a particle which is localized within a certain region of space can be described by a matter wave whose amplitude is large in the region and zero outside it. It means that where there is higher probability of finding the particle, in that place the amplitude will be large and it will be zero outside of that region. So we have to construct a wave function in such a way so that we can describe the matter wave in such a way whose amplitude is large in that particular region where we can find the particle and it will be zero outside of that position. This matter wave must then be localized around the region of space within which the particle is confined. So this concept is very important, that the matter wave will be localized around the region of space within which the particle is confined. So a localized wave function is called a wave packet. This is the concept of the wave packet. So what is wave packet? A localized wave function is called a wave packet. Now how we can localize a wave function, that I will discuss later, but the concept is very important, that is wave function corresponds to a wave packet corresponds to a localized wave function. A wave packet therefore consists of a group of waves of slightly different wavelengths with phases and amplitudes so chosen that they interfere constructively over a small region of space and destructively elsewhere. So this is the physical concept behind the construction of the wave packet. Wave packet therefore consists of a group of waves. So it is not a single wave. As the name suggests that this is a packet. Packet means there will be a group of waves of slightly different wavelengths. So wavelengths of those waves will be slightly different. And what will be the phases and amplitude? We have to choose the phases and amplitudes of those waves in such a manner so that they interfere constructively over a small region of space. Why small region? Because in that small region, the probability of finding the particle will be high. So they will interfere constructively over a small region of space and destructively elsewhere. Why destructively? Because in those positions we cannot find the particle. So the waves will interfere destructively elsewhere. Now I will discuss about the concept of localized wave packets. So how we can construct the localized wave packets. The localized wave packets can be constructed by superposing in the same region of space waves of slightly different wavelengths as we have already discussed, but with phases and amplitudes chosen to make the superposition constructive in the desired region and destructive outside it. So how we can construct such a localized wave packet? This is the basic question. Mathematically, we can carry out the superposition by means of Fourier transform. So we have to take the help of the concept of Fourier transform to construct such a localized wave packets as we are discussing. For simplicity, we are going to consider a one-dimensional wave packet. So the wave packet is one-dimensional in nature. This packet is intended to describe a classical particle confined to a one-dimensional region. So we are thinking that a classical particle that is confined in a one-dimensional region. That is, the particle can move in a particular axis. For suppose it is moving along x-axis. So the particle, classical particle which is confined in a one-dimensional region and the particle is moving along the x-axis. We can construct the packet. We are assigning the packet as psi xt because the packet is ultimately a wave function. We are describing the wave function in terms of wave packet, but we are using the notation of the wave function psi xt. So our aim is to describe the wave function in terms of the wave packet. So the wave packet is psi xt and we are describing psi xt by superposing plane waves which are propagating along the x-axis of different frequencies or wavelengths. So psi xt is the superposition of the plane waves of different frequencies or wavelengths. So what is the mathematical uh, interpretation of psi xt? Psi xt is equal to 1 by root 2 pi integration minus infinity to plus infinity phi k e to the power I kx minus omega t dk. We know that a plane wave is described by the function e to the power I kx minus omega t, and this phi k is the amplitude of the wave packet, and psi xt is the Fourier transform of the phi k and vice versa. And here k is the wave number. In what follows, we want to look at the form of the packet at a given time. We will deal with the time evolution of the wave packets later. That is how the wave packet changes with time, that will be described later. At first we have to choose the time t is equal to 0, and later we will observe that how the packet modifies with respect to time. So we can at first time choose the time t is equal to 0, and for t is equal to 0 the wave function psi xt or the wave packet psi xt can be written as psi x comma 0 or psi 0 x. So psi 0 x we can write in this way, that is 1 by root 2 pi minus infinity 2 plus infinity phi k e to the power I k x dk. You see that in equation 1.94 we have just put t is equal to 0, and we have obtained equation 1.95, that is the equation of psi 0 x, that is the equation of the wave packet at time t is equal to 0. Here phi k is the Fourier transform of psi 0 x. We can write phi k is equal to 1 by root 2 pi minus infinity 2 plus infinity psi 0 x e to the power minus I k x dx. This relation, that is 1.95 and 1.96, these two equations show that phi k determines psi 0 x and vice versa. That means we can determine phi k from psi 0 x, and we can also determine psi 0 x from the equation of phi k. The packet which is described by the equation 1.95, that is psi 0 x, whose form is determined by the x dependence of psi 0 x, does indeed have the required property of localization. So how we can understand that the equation 1.95, that is the equation of the wave packet, is localized or not? How we can understand? So it can be understood in this way, that there is a function e to the power ikx in the integrand. Now if we take mod value of psi 0 x, so it peaks at x is equal to 0, because at x is equal to 0 value of the exponential function will be 1, that is maximum, and vanishes step by step far away from x is equal to 0. So for x is equal to 0, value of the integrand will be maximum, and for other values of x, ultimately the integrand step by step it will become 0. So on the one hand, as x tends to 0, e to the power ikx tends to 1. Hence the waves of different frequencies interfere constructively at that position. That is, the various k integration in 1.95 add constructively. On the other hand, far away from x is equal to 0, when we move either right side or left side to the position of the x is equal to 0, that is mod of x very greater than 0, the phase e to the power ikx goes through many periods leading to violent oscillations, thereby yielding ultimately destructive interference. That is, the various k integration in 1.95 ultimately give the 0 values. This implies, in the language of Born's probabilistic interpretation, that the particle has a greater probability of being found near x is equal to 0, and a scant chance, that is a small chance, of being found far away from x is equal to 0. So this is the way in which we can construct a wave packet with the help of Fourier transformation. So in summary, we can say that the particle is represented not by a single de Broglie wave of well-defined frequency and wavelength, but by a wave packet that is obtained by adding a large number of waves of different frequencies. So the main conclusion is that we are not describing the particle in terms of a single de Broglie wave, which we have studied in the de Broglie's hypothesis, that is lambda is equal to h by mv. That lambda is a single wavelength. But in the concept of wave packet, we are describing the particle in such a way, that is there is a superposition of large number of waves of different frequencies. So wave packet is constructed by adding a large number of waves of different frequencies instead of a single wavelength. The physical interpretation of the wave packet is that psi0x is the wave function. So what is the interpretation of psi0x? Psi0x is known as the wave function or the probability amplitude for finding the particle at the position x. We are assuming t is equal to 0. So what is psi0x? Psi0x is the wave function or the probability amplitude for finding the particle at the position x at time t is equal to 0. Hence, mod of psi0 x square gives the probability density. What is mod of psi0 x square? That is the probability density for finding the particle at the position x at time t is equal to 0. So what is the significance of mod of psi0 x square? That is the probability density, and we can write it as px. But px dx, that is equal to mod of psi0 x square dx, gives the probability, that is the simple probability of finding the particle between x and x plus dx. Now we will see the graph of the wave packets. So we have already discussed about the mathematical formulation of the wave packet, and we discussed that wave packet can be constructed by the superposition of different waves of different wavelengths. Now, how the graph will look like? The first graph shows the mod of psi0 x square as a function of x. So, in this case, we have considered the packet as Gaussian in nature, and we have shown a typical example of psi0x, and the example is the Gaussian function. Here psi0x is equal to 2 by pi a square to the power 1 by 4 e to the power minus x square by a square e to the power I0 k e to the power I k0x. This is a Gaussian function of the wave packet psi0x. So this will look like this, and it can be shown easily that at the position x is equal to 0, mod of psi0 x whole square is the highest here at the position x is equal to 0. And as we move far away from x is equal to 0, the step by step the value of psi0 x whole square is decreasing. And this is the width delta x for the wave packet. This is called the half width of the wave packet. Half width is defined in such a way that the maximum height decreases to 1 by e in this position. This is the half width delta x. And similarly, we can also describe phi k. So if we plot phi k whole square as a function of k, so the graph will look like this. At a particular position k0, we will get the highest value of phi k square, and as we move far away from the k0, the height of the wave packet decreases step by step. So this is the graph of phi k whole square, and we have assumed the structure of phi k as Gaussian in nature. So phi k is equal to a square by 2 pi to the power 1 by 4 e to the power minus a square k minus k0 whole square to the power divided by 4. So psi0x peaks at x is equal to 0 and phi k peaks at k is equal to k0 respectively, and vanish far away from this position, that is x is equal to 0 or k is equal to k0. So these are the graphical representation for the wave packets. Now, from the equation 1.95 and 1.96, where we have described the mathematical expression for the psi0x and phi k, we can again see those equations, that is 1.95 and 1.96, the mathematical expression for the psi0x and phi k. And from this equation, if we take the mod values of psi0x and mod values of phi k, then we can easily show that minus infinity to plus infinity, mod of psi 0x এর whole square dx is equal to minus infinity to plus infinity mod of phi k square dk. So from those mathematical expression, it can be shown that the integration which runs from minus infinity to plus infinity, and if we take the mod values of psi 0x and phi k, so we can show that minus infinity to plus infinity mod of psi 0x এর whole square dx, that is equal to minus infinity to plus infinity mod of phi k square and dk. So what is the meaning of the equation 1.97? The meaning is that if psi x is normalized, so is phi k. So if psi x is normalized, phi k will also be normalized. Thus, the function phi k can be interpreted most naturally like psi 0x as a probability amplitude for measuring a wave vector k for a particle in the state phi k. As we are saying that psi x is the wave function at the position x at time t is equal to 0 for the particle which is propagating along the x-axis. Similarly, we can also interpret that phi k, this is also wave function, but it is in k space, and phi k represents the probability amplitude for measuring a wave vector k for a particle in the state phi k. Moreover, while phi k whole square, mod of phi k whole square represents the probability density for measuring k as the particle's wave vector, the quantity pk dk is equal to phi k whole square dk gives the probability of finding the particle's wave vector between k and k plus dk. So as psi 0x and phi k are related, so similar physical significance can also be given for phi k as we have described psi x. We can extract information about the particle's motion by simply expressing its corresponding matter wave in terms of the particle's energy E and momentum P. So, we can describe the matter wave or the wave packet in terms of the energy and momentum. We have already shown that is how to describe a wave packet. In equation 1.95 and 1.96, we have interpreted the wave function in terms of x, that is the position, as well as in terms of the wave vector k. Similarly, the wave packet can also be described in terms of energy also. So how to describe the wave packet in terms of energy? For that purpose, we have to use some relation. That is, we know that P is equal to h cut k or k is equal to P by h cut. So dk is equal to dp by h cut. We also know that E is equal to h cut omega, and we are defining phi k by root over of h cut as phi p. So this phi p is actually the momentum amplitude. As we were saying phi k as the amplitude corresponding to the wave vector. So similarly, we are saying phi p as the momentum amplitude. And if we use these relation, then equation 1.94 and 96 can be rewritten in terms of the following equation. So you see that the wave function or the wave packet psi xt here has been written in terms of energy and momentum. Equation 1.98 describes the wave packet in terms of momentum p. You see that momentum p is here in the right hand side, as well as energy is there. So equation 1.98 describes the wave packet in terms of energy and momentum. And similarly, at t is equal to 0, we can describe the wave packet as psi 0x. So we have just used t is equal to 0 here. Here psi 0x has been written in terms of the momentum. So these are the energy and momentum representation of the wave packet. Now I will discuss about the wave packets and the uncertainty relation. So how we can get the idea of uncertainty relation from the concept of wave packets. We want to show here that the width of a wave packet psi 0x and the width of its amplitude phi k are not independent. They are correlated by a reciprocal relationship. As it turns out, the reciprocal relationship between the widths in the x and k spaces has a direct connection to Heisenberg's uncertainty relation. We have already described how to calculate the widths in the x and k spaces in this graph. So let us look at the graph again. This is the graph of mod of psi 0 x whole square, and this is the graph of mod of phi k whole square. This is the width delta x. This is called the half width. So half width means where the amplitude decreases 1 by e times its initial value. If this is the maximum amplitude, so in this position the amplitude will decrease to 1 by e of its initial value, and same for the, that is, graph in the k space also. This is delta k and this is delta x, and we are saying that delta x and delta k, they are correlated, and the reciprocal relationships between the widths in the x and k spaces has a direct connection to Heisenberg's uncertainty relation. We will show that the relationship between the delta x and delta k is reciprocal in nature. We will show this by using the equations which we have already used earlier. So we are considering the wave packet is Gaussian in nature. In the graph that we have described earlier, in that graph we have used the Gaussian wave packet, and the equation of the Gaussian wave packet was psi 0 x is equal to 2 by pi a square to the power 1 by 4 e to the power minus x square by a square e to the power I k 0 x, and this is the equation for the phi k in Gaussian format. So in that figure, mod of psi 0 x whole square and phi k whole square are centered at x is equal to 0 and k is equal to k0 respectively. It means at the position x is equal to 0 and at the position k is equal to k0, the amplitude for the psi 0 x whole square and phi k whole square was maximum. It is convenient to define the half widths delta x and delta k as corresponding to the half maxima of psi 0 x whole square and phi k whole square. In this way, when x varies from x is equal to 0 to plus minus delta x, or k varies from k0 to k0 plus minus delta k, the functions mod of psi 0 x whole square and mod of phi k whole square drops to e to the power minus half. So mod of psi plus minus delta x comma 0 whole square divided by psi 0 comma 0 whole square e to the power minus half. This means that whenever we are going plus delta x or minus delta x from the position x is equal to 0, mod of psi plus minus delta x comma 0 whole square divided by mod of psi 0 comma 0 whole square is equal to e to the power minus half, and similarly for the k space also. So these equations combined with equation 1.110. 1.110 means that is the function psi 0 x and phi k. So we have this function psi 0 x is equal to this one. Now if we put that value of psi 0 when x is equal to plus minus delta x, so t is equal to 0, so this function we will use, and we will use this function for the position plus minus delta x, x is equal to plus minus delta x, and for x is equal to 0. So at first we will calculate the value of psi 0 x for the position x is equal to plus minus delta x, as there is x square here. So value of the plus minus delta x will be same, and we are taking the mod value, so this function is not needed here. So if we put the values for the position x is equal to plus minus delta x and for the position x is equal to 0, and if we put those values corresponding to e to the power minus half, then you will obtain that is delta x is equal to a by 2. Similarly, if we use the function in k space and if we proceed similarly, that is if we calculate the value of phi k at the position plus minus delta k and for the position k is equal to k0, then we can using equation 1.110 and 1.111 we can show that delta k is equal to 1 by a. So using these two equations, that is 1.110 and 1.111, we can show that delta x is equal to a by 2 and delta k is equal to 1 by a. So if we multiply them, we are obtaining delta x delta k is equal to half. Since delta k is equal to delta p by h cut, so we can write the above relation in this way, that is delta x delta p is equal to h cut by 2. This relation shows that if the packet's width is narrow in x space, if the packet's width is narrow in x space, its width in momentum space must be very broad and vice versa. So the relation between delta x or the relation between delta x and delta k or the relation between delta x and delta p is reciprocal in nature. So if the packet's width is narrow in x space, that is if delta x is narrow, its width in momentum space, that is delta p, will be broad and vice versa, as the relation is reciprocal in nature. Now a comparison of equation 1.114 with Heisenberg's uncertainty relation. Heisenberg's uncertainty relation is delta x delta p greater than equal to h cat by 2. So if we compare this relation with the Heisenberg relation, it can be seen that the Gaussian wave packets yields an equality. So Gaussian wave packets yields a equality as seen from the equation 1.114. There is equality sign here, not an inequality relation proposed in the Heisenberg's uncertainty principle. In fact, this equation is the lowest limit of Heisenberg's inequality. So if we consider the packet is Gaussian in nature, then we will obtain the minimum uncertainty wave packet. So this is the lowest limit of Heisenberg's inequality. That is the equation described here, equation 1.114. This is the lowest limit of the Heisenberg's inequality because we have assumed the wave packet is Gaussian in nature. All other wave packets yields higher values for the product of x and p uncertainties, that is delta x delta p greater than is equal to h cat by 2. So in conclusion, we can say that the value of the uncertainties product delta x delta p varies with the choice of psi, but the lowest bound h cat by 2 is provided by a Gaussian wave function. So this is the end of the lecture. I will request the viewers to go through the textbook of NGTL for further understanding about the concept of wave packet. Thank you all for listening the lecture.